Good morning, all. A hearty welcome to Dr. Alex James, and I am honored to brief about Dr. Alex James. Dr. Alex James is working as a professor in electronics engineering at Digital University, Kerala, and as the chief scientist and CTO at Graphene Aurora. He led the research and development of cutting-edge graphene-based devices and neural chips for various applications such as biomedical, IoT, and AI. With over 20 plus years of experience in the field of electrical and electronics engineering, he had developed multiple patents, publications, and products that have advanced the state of the art in brain-inspired computing. Areas of he is currently working in the areas of AI chips like memristors, crossbars, neuromorphic circuits, ANN, SNN, CNN, LSTM, HTM, LLMs, RF circuits, antenna designs, and so on. He's working, his expertise is also in RF circuits like antenna designs in UWB, phased array antennas, parabolic antennas, horn antennas, log periodic, patch antennas, Yagi-Uda, and spiral antennas also. And he's working on various 2D materials like graphene and memory circuits like RAMs, STT RAMs, PCMs, and also working in drones, image processing, AI/ML learning circuits, security circuit, impedance matching, and crosstalk and signal reflections, jitter and timing analysis. So we are very happy to have a versatile speaker here with expertise in various fields. And we are honored to call upon you for your talk, sir.
You know, when I started working in this field, I started with memories. So my career started with memories. And one of the first memories, we started to build was silicon carbide based memories. I'm not sure whether you know it. Silicon carbide based memories do exist. So we used to, spend a lot of time in clean room trying to figure out how the, it could be made real. So it's a very simple diode-like structure that we were working on, but it was very, very difficult to get a uniform PN junction, which would be defect-free. So while we were doing that, I could see something like, a layer of carbon getting formed. And that was, we always thought this was a useless thing. And that was today known as graphene. Okay. So this was way back in 2003, and at that time, graphene was not really discovered and things like this, but we always used to remove that. And those memories, we then started, I started a company. We wanted to create memory, but instead what we got is a PN junction and a LED. Okay, so if there are people who are aspiring to be entrepreneurs after PhD and things like this, one thing you would see is you start with something, but your real success may be in something else. Okay, so that's that's the truth of it. And over the years, many, I have zero background in programming, but I ended up writing almost thousands and thousands of lines of code, right? So that's another interesting learning that, as an electronic engineer, you need to be better than a computer engineer if you want to get anything done. So I tell this to my students all the time, if you want to be a good electronics engineer today, you need to have from devices to systems, you need to be trained. It can't be that you're just doing devices and you'll see at the end of the day things happening in real. So part of it is this story as well, when we wanted to create memories, we wanted to find useful application around those memories. So usually a device physicist or my supervisor, back then, he was originally, I think he is Serbian, but who, long time, he lived in Australia and I did my studies there. So at that time, and his heritage was a Russian heritage. And you know how the Russian people are, they don't change their opinion that easy, right? So we would argue every day on something, and he will not agree and I will not also agree. And this went on for quite some time. For everything we used to debate, and it used to be quite useful. Although many of these things did not translate to actual research work, it actually helped in a longer run to come up with a lot of ideas. And so many of the ideas, over the years, things started from there, and so some things that were partially incomplete or something that you would want to pursue, then and later you end up doing it. So devices, memories, we want to have something more than just a storage. So we started looking at a lot of different things beyond beyond electronics. So one of the thing was looking at intelligence itself, looking at the natural world and seeing what is the intelligence, where is this intelligence, where is this memories. So one interesting thing was these many of natural world or systems out there, they don't have neurons. They practically don't have neurons, but still they are able to do interesting things. So if you see mycelium networks, right? It's a fungi, and it has memories. It remembers, and it can move and create spatial patterns. And no matter where you put it, it will follow certain patterns. You have slime molds, which also has a very interesting spatial memory. You put on any surface, it adapts to that particular surface, and it actually moves in a particular way. The complexity of it is also quite fascinating. You can in fact model most of these things as state equations, and then try to understand the dynamics of it, and see how these patterns are formed. This is another example, Venus flytrap, right? Very famous, popular. Insect sits on it, it will just catch it. Another insect comes in, it already knows that there was a previous insect. So there is a sensory mechanism and there is a memory mechanism. There is a processing happening. So as something that you would think plants which would not have any intelligence, it's exhibiting a certain level of memory, certain level of processing and things like this. Then moving from that, if you look at insects, right? Insects have very few set of cells. Bees have a lot of eyes. I don't know whether you know this. If you go back to the biology lessons, you would see a lot of eyes, and each eye requires images to be processed. And this is they do much better job than a lot of our image processing algorithms, right? So it's able to imagine you place 100 cameras and then ask to do some processing. And these guys have hardly few neurons, and it's able to do much more. So then you start to wonder, where are we going wrong? It's a sensory processing and things like this. It's able to do a lot more. So one thing is, memory is very much fundamental to intelligence. That's what it tells. It tells the architectures that we are dealing with, in terms of ALU and memory as a separate block, may not be the way to go about. And that's where the whole idea of in-memory processing comes into picture, where we don't see ALU and memory as a separate unit. We just see everything as just same. It's just memories. And can we use these memories for processing? Can we use these memories for storage? Can we use it to emulate intelligence, and so on and so forth? It's a fundamental question. Now there are also other reasons to go in that direction. If you look at a comparison of neurons, right, the number of synapses in a human brain is over hundreds of trillions, and operations per second 10 raised to 16. Look at the power numbers, 20 watts. Look at the supercomputer numbers. It's you cannot put a figure there, because each NVIDIA adds on another tons. So in terms of power, there is absolutely no comparison. So biological systems, even as simple as like, a bird brain is much, much better than most of the supercomputers out there. So that's what we are dealing with. Like, no offense to computer science people if there are any, but you're doing things very wrong. That's not the, and I can show it like, a bit more detail. Like, so processing power, human brain, 1 exaflop, right? Energy efficiency, 20 watts. Learning ability, it's highly adaptable and flexible. Memory capacity, 2.5 petabytes. Adaptability, easy to adapt in any new environment. Parallel processing, it's 86 billion neurons, exceptionally parallel. If you look at processing speed, it's very slow, right? So with just 200 hertz, it's able to do all these magic, right? And we are pushing for clock speeds. We are pushing for all sort of like, designing amplifier this and amplifier that, which would like, has to push all the boundaries. But our poor brain, 200 watts, it's able to do much more. If you look at data transfer, again very slow, 100 milliseconds, right? Milliseconds. Error handling, it's very much like, fault tolerant. Half of your brain cells are dead, you are still alive. You can still think. You do the same thing, take a processor, kill half of the circuits. Forget half, 10%, gone, right? Then we are having, different types of sensory inputs, whether it's touch, whether it's like, vision, hearing, all sort of things. Pattern recognition, highly efficient. We don't know anything better than brain for doing that. Creative ability, abstract thinking is very high. Consciousness, like, that's something that people still try to figure out what it is. Then physical size, only 1.4 kg, right? Laptops are heavier than that, right? So repair and maintenance, it does it by itself. You don't need a doctor to fix it, right? A lot of these things, you don't need like hundreds of debugging engineers. It does by itself. Connectivity, 100 trillion synapse. So energy source, easily, plenty available. It's all basic food. Can you feed a computer with dal and chawal? Not going to happen, right? So we have fundamentally a lot of different things we need to look at if you want to compete with brain. That's the first thing that you will see. And even the things that we see as like disadvantage may not be disadvantage. Like, here, like, for example, natural language is ambiguous. Now, the whole question of like, do we want to create like computers all which can understand the same language, or can it understand multiple languages? That's a entirely different question, right? So we as a human society, we can understand hundreds of different languages. But the way like we process the information is also very different, and we can still do many different things. But the way we build the computers, we limit ourselves to certain set of languages, and we say, okay, this is how it should be. For example, it should be only binary. Who is stopping us from not building something outside binary? We didn't really. Can you have like analog languages? Can you have like discrete languages, not just limit to binary language? So all sort of things are there, which makes it interesting. So from our point of view, like we were looking at memories, and one of the looking at memories, there were many different memory options out there, from SRAM, DRAM, to RERAMs, to all sort of things. So we wanted to have something that is very simple, two-terminal, like a resistor. So we went with first thing was RERAMs, or otherwise known as memristors. So there is a class of devices. It's not just one device we are talking about. There is a class of devices which can be categorized into resistive change or resistance-based like memories. So what is this like, in memory processing? How do you do that with an RERAM? Imagine it has a resistor, a nonlinear resistor, right? A nonlinear resistor means like, you can have multiple resistance using the same device. So it's, if it's a linear resistor, you have one resistance, whereas if it's a non-linear, you end up having multiple resistance. Now imagine a crossbar structure like that, where you have columns and rows, and between the columns and rows you place these resistive devices. So each node in that, one side you have the row metal going in and you have a column metal going in, and the device is sandwiched between those two. So if you see there the dotted lines, it just shows the flow of current. So if you apply like a row, like a voltage, you have resistance, resistive device there, which you can assume as conductance. So if you have voltage multiplied by conductance, what do you get? Ohm's law gives you current. Now if I have every row a voltage applied, and each node you have a conductance going in. So basically what I am doing is summation of currents in the column. So that summation of currents is nothing but weighted summation of input with conductance value of these devices. Or it's essentially, if you simply say, it's a weighted summation of inputs. Where have you heard about this word weighted summation of inputs? Neural networks, right? So each neuron you can basically emulate as one column of these crossbar. Now weighted summation is also very frequently observed in many other things. When you do linear algebra, what do you see? Weighted summation. When you do convolution operation, you see weighted operation. So weighted operation is something that you would see in across many different fields, which also means, like, I can now think about, like, implementing many of these applications with these crossbars. Okay. Now the best thing is, or the worst thing you can say, if you are these are currents are all analog, input can be digital or analog, right? So we are doing analog compute. So our neuron model here is purely an analog based like system. The size of these devices are like 5 nanometer, or you can even scale it down. It's a filamentary device, so it's extremely small. So area wise on chip, you are actually having really small arrays compared to, like I say, if you want to do a weighted summation, it's basically a multiply and accumulate operation or MAC operation. Multiplication in digital will be very large. If you have 32-bit, that many number of adders, or that you are looking at. So you can actually, like, do or get away with like a lot of computation in extremely small area on chip. So that one single crossbar essentially shows one column of, or one neural network, say one layer of neural network. Essentially it's a single layer of neural network. And output of this, I can take it to a RULU or like a sigmoid, and that completes the network, right? Your activation function. So about a decade before, DARPA had a challenge where they said, okay, let's have these kind of crossbar synapse built, and eventually let's build an electronic brain with it. So over a decade, like, a lot of work has been done. Many research has progressed quite a bit. Whether do we have a brain yet? Probably not, right? So it's still like, a bit of a challenge. So this field, if you look at, like, if I have to simplify the AI chips field, like, it's not just analog, you can also do things in digital. So there are two parts to it, like in two different branches you can say, which people are working on. One is AI accelerators. Accelerators mean, like, you have a traditional neural network like LSTM or CNN to all these neural networks, which you try to implement in hardware to improve the energy efficiency, performance, speed, all those sort of things. And two approaches to it, one being purely a digital based solution where you use like FPGA or GPUs or SoC based designs, or mixed signal, mostly, like, we are looking at, like, ReRAM based solutions or MOSFET based solutions. We, all sort of different memories being used, from floating gate devices to something like, SRAM, DRAM, even transistors are used to build those arrays to do those computations. Then you have the other part of the story, which is like general purpose AI. So general purpose AI is a bit more, a bit more thinking for the future, right? So we are looking at like how can you make the system more general? Can you build like systems starting from LLMs to bio-inspired systems and so on and so forth. So today, like people have fabricated LLM in a chip. It's called wafer level, not chip level, because the size of the chip is like this big, right? So if you want to put like a trillion parameters in a digital, like that's the area that it takes. So you need like a 12-inch wafer, and almost like that a wafer is full of this particular like circuits going in. We are also looking at mixed signal systems where we can reduce that area. So recently we had like one work that we showed like where you can have like a spiking based LLM implemented on chip, which you can like really reduce the area and all those things. So the whole field of like memory based or ReRAM based computing started way back. Professor Leon Chua started that with a simple question, asking, okay, there are all sort of these elements, capacitor, resistor, inductor, they are all related, right? So voltage is related to charge, voltage is related to current, current is related to flux. You all have devices for it. Then why not like flux and charge? Where is this device? Where is this elusive device? Like, if it's a fundamental quantity, then it has to be related as well. That's how the whole idea came, and this is the IV characteristics of such devices. And you can see it's frequency dependent. The change in the frequency, it will change the resistance of these devices. And that sort of plot is known as pinched hysteresis plot. Pinched meaning like, it crosses over the zero. When current is zero, voltage is zero, voltage is zero, current is zero, depending on whether it's a voltage or current control device. And you can model it as a state equation. So a state dependent Ohm's law. So if you look at their I equal to G, X, V, V, where X is a state variable, and dx by dt equal to f x v. So it looks very similar to a control system, right? If you learn nonlinear control, you would see like, it's exactly this. Only thing, the function here is like varying, and the function here is nothing but a device we are modeling. And if you plot a dynamic root map or the phase plot of these, you can actually understand the dynamic behavior. Now, what can you do with it? Simply because you can understand the dynamic behavior, like you can actually see when the system is stable, when the system is unstable, when it's like edge of chaos, and so on and so forth. And there is a very famous circuit that is built, like Chua's circuit, and it's considered as one of the nonlinear circuits, like one of the primary inventions, which has led to all sort of chaotic circuits. So the entire field of chaotic circuits was built on this particular concept, that you can actually look not the devices, the circuits as not just all stable, but you can also find those regions which are unstable, which are stable and unstable at the same time, which is known as edge of chaos. And interestingly, a lot of these neurons behave in edge of chaos. So our cells, if you try to model, like they are all like behaving this edge of chaos where it can be stable and unstable. That's why it's able to fire. Neurons are able to fire and things like this. So all these modeling can be very easily figured out. So we are using that thing to construct those neural networks, right? So we have each column of crossbar representing a neuron, and a crossbar like that represents the neural network, and you can actually implement the softmax as well. Simple way to implement the softmax is use a winner takes it all circuit. A WTA does the job. So if you want to have entire like thing in analog, you can simply do it, right? So you can have the directly to the image sensor, you can connect your crossbars like this, put a WTA, and you can have recognition, everything happening all in a single chip. So sensor based processing and many other like edge computing can be done like extremely efficient without having the need of A to D converters, filters, or any of these things. You can directly interface. And this is one of the things that we did. There was a collaborative work with Oxford, and we basically showed you can have image sensors where you can do image processing, object detection, and all those things, all done along with the sensing. Now there are a lot of challenges that is there in this, when you are trying to think on a practical scale, right? If you are just doing simulation, it works fine. But if you want to build a product, if you want to make sure it works, then you need to reorient the thinking slightly different, right? So usually what happens is people start with algorithm and then they try to translate that into the hardware. Most of the time this fails in hardware because any kind of these analog hardware, they are process dependent, they are technology dependent. There are a lot of these practical issues that come by, which makes it important that when someone writes an algorithm, they also have an understanding about the hardware. So hardware software co-design is quite an important thing in this field. So there are all sort of this event-driven processing that happens, learning and adaptation algorithms. All of these things needs to be looked from the eye of a hardware, not from the eye of an algorithm. Now, why hardware is important? Because you want to ensure the energy efficiency is high, integration density, whether you would use a process technology which would support a 3D integration, or whether you would use a chiplet, whether you would use any of those things to really pack or increase the density comes into play. Device technology becomes important. When you are looking at many of these devices, they have all sort of different variabilities to it. And variability data, none of the companies will provide you, because obviously, they don't want you to feel like their technology is bad. So they will never give you that. So you need to, as a researcher, have to go and figure out all those things. So that's why the third part becomes very important, all the environmental conditions, real-time processing requirements, everything needs to be analyzed. So it's a cycle between these three things that happens. Now, when talking about variability of these devices, there is device-to-device variability that happens. There is all sort of different possibilities. Like IBM has a PCM, which is proprietary to IBM. They have run more than 1 million tests. They are put out models and things like this that researchers can use. But then there are RERAMs already in the fab now. If you look at TSMC or Global Foundry, all of them have RERAMs which you can use. So there are devices, but these devices have got those variabilities. Now, if you want to model it, there are again many different ways in which you can model, from physics-based model to data-driven models, to just purely you're looking at mathematical models, everything to come in. Some of the things that you would have to consider in this is aging, reliability, read instabilities. Conductance drift, some of the devices will show. What it means is you keep the device on for some time, automatically even if you remove the power supply, the conductance starts to change. So this is partly an aging effect, partly this is a effect of the device itself, how it is manufactured. Then you have interface electronics. Most of the research papers would not talk a lot about interface electronics. Okay, my guess is that most of them don't know how to do it. Okay, because this is basically 80% of your chip. Okay, the crossbar part is the is one part where you can put the logic and all those kind of things, but then someone has to program it, right? You need to update the weights. You need to keep on tracking that the conductance, everything is as you imagined. So there is a lot of those logic that goes around the arrays, and that needs to be figured out, and each of them it has its own challenge. So just to give you a sense of with variability in analog, what happens. As a network, there is not a huge impact, right? So if you look at the variability, even 10%, 20% of many of these changes, you program these, reprogram the weights, you would see it's fairly tolerant. The variations like in accuracy is not much. It's 1%, 2% drop. Where it has the biggest impact is one is on the number of conductance levels or stable conductance levels each of the devices will have. So if, what does it mean? You take a memristor, it can be programmed to 2 resistance level. So it becomes 2 state. If you program it to 16, then that is 16 state. So that is the number that is shown there, levels. How many stable conductance levels are there per device? So if you see here, if it's only 2 and if you use it analog, obviously there is no, it's all binary weights and the accuracy will come down. If you are having say 16, you can see it's as good as like software level performance that one would get. So which means the highest impact that one is having is the conductance levels. Now obviously devices would have this limitation. When someone makes a device, like they would say I will have 16 or I will have 8. So that is going to be one of the major limitation and something that needs to be overcome. So I'll come to that. So anyway, along with this, you also need to program these, reprogram, learn, right? So there are many ways to learn. You can actually like use your algorithms to back propagation to learn and identify those weights, convert those weights to conductance values and program these networks. So then we had this wild idea, let's put like software engineers out of job. We created like a chip which can do the learning by itself, right? So have the backpropagation also inside the chip. So now we have a chip which can automatically do the learning. We can basically like have the arrays programmed, everything in a single chip. The only limiting factor here is the endurance of the memory, right? So you need to have high endurance. So you write, rewrite, erase, like that cycles it needs to tolerate. So if you have a device which is like very less very low endurance, obviously it will fail. But if you have high endurance, like flash memory, it can work for long. So programming is usually like one-time business. So once you do the programming, then it's only inference. And inference is like only read operation. So there is no, even if you only have like 1,000 cycles left, it is still fine. You can run it for a long period of time. And part of it is also to ensure that these networks, when we analyze, because everything is an analog, okay? The entire thing is an analog. There is not single digital circuit. I mean, even if there is just a circuit level. So that is what one of the main difference that you would see. Like people have done programming part in digital, right? Because they put a RISC processor or they put like some of the microcontroller IPs and then use it for sending the control signals and programming. So this is we thought like that is very inefficient because of the area that it takes. But if you can do everything in like it's just gradient operation, and this gradient operation if you can implement on analog, it's going to be much less in terms of area, and it's actually much less in terms of area. So now the next challenge is to look at the uncertainties and figure out like failures. RERAMs is a memory, it can have all sort of failures. And there are 4 types of failures that are possible in terms of the conductance value increasing, decreasing, or like combination of both. So for those, again, like we need to do an analysis. So before you basically build your architecture system and things like this, so because in the past, like I had gone through the pain of like learning the programming language and all these things to write code, everything, and I realized like most people are not interested in doing that. So what we did, we created a GUI for all these lazy engineers to just like drag and drop to introduce them into the field, right? So good sense of, is your network going to be useful for the hardware, or what kind of resistive networks and what kind of sigmoid functions, all those things. Now we'll come back to the problem. One of the biggest problem that we had in this field is this one, the levels. Number of levels are very low. So during COVID time, I had practically nothing to do. So I did this, right? We looked at you know, when everyone was like, you know, entire, you know, some of the good things happen when there is like all these kind of situation like COVID, right? So everyone is like tensed and you know, you don't know what. So during that time, like, you know, we just looked at this crossbar arrays, tried many things, and finally a solution to this number of levels. All you need to do is just tie up the rows. Okay. Now just tying up these rows, what do? You basically connect two resistors in parallel. Right? When you connect two resistors in parallel, and each resistor able to take n number of levels, right? Then the effective resistance that you have is you have many different combinations. So, and that combination interestingly follows geometric series, geometric patterns. So we found it is simplical numbers, right? It's basically geometry, vortexes. You just count the vortexes, and you can see if you have just eight devices in parallel connected, each having only 12 levels, effectively you can create 75,000 stable levels. So with just 12 levels, we are able to actually create almost 75,000 levels. Now that's interesting, right? Because, you know, we don't have to worry about device physicists anymore. As a circuit engineer, you know, reliance on device guys are then reduced, right? Because you put a lot of money into the foundry, you know, trying to figure out like, you know, stable devices and stable devices. Now we have an approach where we are saying, okay, you give us whatever you have. We'll create like, you know, effectively better stable devices. So aging doesn't matter to some extent, like, you know. So the thing is, like, with aging, what happens? Some of these levels disappear. So instead of 75,000, you will get 12,000, you know, say 1,000 even, you know, over a period. Still, 1,000 is good enough. So if you are looking at, you know, all you need is more than 100, you know, 60 levels. So the reliability in terms of actual circuit like increases like anything. So even when the devices are like having variability, even when it's unstable and so on and so forth, we are having a situation where we can create like neural networks which are fairly stable in analog. Then if parallel thing work, then, you know, first year of engineering taught us, you know, Wheatstone bridge is also interesting thing, right? So then why not? Because Wheatstone bridge is even more interesting, right? So you have two voltages across, and you can have balanced and unbalanced bridge. When you have balanced and unbalanced bridge, you can have even more number of combinations possible now. You have parallel and series combinations happening of the resistors. As expected, now we can see like the previous network was the blue one, and the bridge is now the red one here, number of levels that it can produce. So we see like, you know, millions of levels that you can actually produce with a Wheatstone bridge with just two control signals. Now we need to find some practical applications to it. So we created these networks. With large number of networks, the programming logic becomes harder. So it's always good to work with smaller arrays, and then have a lot of these smaller arrays and put them together somehow to make the application work. So one example is you can split, say in an image classification problem, you split the image into small regions, a lot of small regions. Each of these regions you connect to a neural network. And then you combine all the outputs of this into another set of neural network, combine it. Now that's called modular neural network processing, right? So that will give you exactly same kind of accuracies and performance as good as like, you know, what you would have with a single large arrays. But this is extremely good for hardware because you don't have to have large arrays. You can have really small arrays to build any kind of like classification, and this is some of the with modular arrays in spiking neural networks to all of these, like we call it like image split neural network architecture, and essentially like, you know, it's a hardware based architecture. If you remember previously I said about convolution operation, Now that's also a thing that you can do. Convolution means filtering, all sort of filtering that you do. So a single crossbar, each column would do one filter, right? So I can have hundreds of filtering done in a single array, all at once. So if you're worried about having like, a lot of filtering to be done, all you need is a single array. So here, all these filtered output are coming from the chip, where, you basically are having only a single array, which is doing all those processing. Now variability is a problem, but variability can be also a good thing. Okay, so there is a whole class of like computing called reservoir computing. So if you have seen that field, the reservoir is basically a random allocation of weights, and then you have a dense network following that. So this is known as also echo state networks, where for these devices which are like, if you don't want to program, it's even good, right? So you have a echo state part, which is completely randomly initialized, so I don't even have to program. I just need to create a network, connect the input. It will automatically take whatever value. And then I only need to do the dense layer, which I would program. And you have a fully functional like ESN implemented. And this one we tested with a condition monitoring real-time system. So it was an interesting problem. That's why we did like, apparently in remote areas there is oil theft happening. Transformer oil is very expensive, so people do oil theft, and you need to monitor the oil level, you need to read the currents and all those things. So all these are sensory inputs. So we took all those sensory outputs, and you cannot modify the transformer, right, because it's already invested. So you need to, so we created like a sensor which can be just a very simple sensor thing for level detection, and then for current readout and all those things, and basically connected to this chip to do the processing. Now advantage is it's extremely low power, which means you don't need external power or anything like that. A coin cell battery would do the trick, and it will run for years. And you can basically do the classification there because the network is so small and that it hardly consumes any power. So and this data, if there is a oil change, like all those changes in various like humidity, temperature, everything, it will send the signal, and you have an app where you can see all those things. So this was implemented with a company called Kel. Another things that you could do is like something like a generative. GANs are very popular and things like this. Where because we had CNN implemented, then we thought like why not put CNNs together to create a GAN, and that basically these are generated by the chip. It's about 3 million devices that go into it, and with that 3 million devices, like a small chip, like you could actually generate like images. Then another thing that we took the same array, we rethought the whole thing. It's a weighted summation, and there is a 1988 there was a paper on Shepard similarity, and it's a very thought-provoking paper. It's appeared in Science on like psychological measure of similarity, and the psychological measure of similarity is exponential of -d. Now, when you look at that, like many of the measures that you have, from cosine metric to all sort of things, try to do like whether it's whitening and all these things, they are trying to do the psychological metric. So then we thought like weighted summation is core to the neural. So then why not like try to build that and see it as a similarity metric. So we did like seeing it as similarity metric. Then the output of it is like winner takes it all. So what we have done is, with this crossbar, a simple nearest neighbor algorithm. Okay, with a metric, which means you can also do metric learning there. You change the weights and all those things. You can have real-time changes, all those things. So you're looking at machine learning to be implemented with something like this kind of network. Recently, we started looking at like RF related stuff as well. So because many of these applications like on-body sensing to analyzing like radiation patterns, we could immediately see some applications. So if you have like images, these radiation patterns can be seen as an image, and I can just have a device which could scan through it and figure out like okay, the variation in the radiation pattern, and then go back and see what is the antenna array that is inside the device. Or in other words, What we are saying is we can hack the devices to see what is the antennas inside the device even without opening the device. So this is what we have done, like here, like, it's we created like arrays of these devices to implement like this classification of those radiation pattern, and this is the chip that was done, where you can capture capture it in image, then do convolution, max pooling, all those operations, do the processing. Then we also recently did like, further to that, like looking at the radiation patterns, like you can put like antennas on body and then look at the changes in those patterns. Now, because you can, when people move, the correlation between those signals also change. So the reflectance changes. So all those part you can actually take in and find. Especially these kind of things are useful in space. So if you are astronauts, like going in, you need extremely low power. You can't like consume, you can't take the image, do the processing and all those things. It has to be done in real time on body itself. So for those, that was something that we could figure out, like when people move and everything. Gesture recognition. Another thing is, like, you could use it to actually build antennas itself, right? So if you want to figure out like the length, the width, height, and or your designs, rather than doing it manually, you can have the algorithms figure it out. So we have basically the neural networks used for predicting the antenna parameters. And this way, this whole thing was done purely with no human in the loop, and you had the antenna designed, tested, and working. Another application that we did was like tumor detection, because you can actually look at this radiation, the reflections of non-tumor and tumor tissues are very different, and it's a very important problem. If you look at like all these MRIs and all these methods are very expensive. Now, first line treatment often, like if you can do by like just a device, it's extremely low cost. Just basically a few antennas and things like this and a chip to go with. Then you can just scan and just detect whether there is some difference in the tissue, and that can be a first line treatment. If a doctor basically thinks like there may be something wrong, just do a scan, and if there is a difference from the normal to those regions, then can recommend to the next level. If there is no difference, it's very sensitive as well. So that is another application. Another thing that we looked at is like having smart antennas. So we had like some substrates which you can print the antennas on the cloth, and from there, like we can actually capture like all sort of things, like the environmental factors, cold weather conditions, and all these kind of things, like especially for sportswear and others, performance of the athletes. Many such things could be figured out in that. I'll skip that. These are another thing that I have to say. I mean, I'm sure you have C2S program here and everything, but don't worry if you don't have those tools, because with open source tools also you can do many things. We have taped out so many different chips which works. So if you don't have like access to tools, that shouldn't be an excuse. Today, like Skywater 130 nanometer process supports it, easily available, anyone can download it. Only thing is you need to know how to use it. It's slightly bit more painful than like using Cadence or other tools, because Magic is not still, your layout may not be that friendly in analog. Digital, it's again like there are tools even which would give you like generated really nice layouts. There is one group in US, like they are like writing Python code to generate your layout, right? So all sort of things are there. And these are like chips which are all taped out, fabricated, tested, and all of them works. So we also have other option. You can, if you want to do analog designs, there is another option to quickly test and validate. There is something called FPGAs, field programming analog arrays. Just like gate arrays, you can actually have analog arrays where you can model many of these analog circuits and see it working quickly to see whether whether this logic works and so on and so forth. And then you can So we had this kit developed mainly for neural computing, where you basically have a set of blocks. We have FPGAs and FPGAs together, create a stack of it, and if someone wants to create a neural network in analog and then see how it works, we could actually observe that. So these are some of the major barriers and design considerations that you can look at. I touched upon a few of them. There are many other things as a PhD researchers or MTech students or BTech students, you can look at, right? So many of my papers I write it with either undergrad students or master students and PhD, and even I had first year undergrad students also being part of transaction papers. Okay, so if people believe that education is a level of education is a problem in research, that's a misnomer. You just need a brain with that many number of neurons working or partly working. Okay, even I'll tell you, we had a program where I don't know whether there are some slides I'll show you that I'll come to that. I'll keep it as suspense. Let's see. Okay. So this is other set of initiative we have. So my team has around 80 to 100 people. It's a large group. Around roughly around 20-25 postdocs are there, working on many different problems. We work from materials to all the way to the applications. Most of it is applied research, and most of it is industry oriented research, and we take in interns all the time. So if people are interested, please feel free to contact us. Only we don't look at your grades, we don't look at your education, nothing. We look at how serious you are, and most of them who has come in, they have I have students from many different institutions in India and outside India coming in, faculties coming in, spending a few months and things like this. We encourage that, because depending on what is your interest, you can do this. And we don't push, one of the rules in our group is we don't push people to publish papers. Okay. So one thing, I ask my students, before they graduate, they need to have at least one startup. That is a requirement that I put. I don't care about their publications and things like this, but if they have it, it's well and good. But if they publish, they need to publish in extremely good quality, top quality places. So that's been the approach. We are creating a graphene, good ecosystem with even a small plant is being set up, where we can actually have various products have come out. Terracotta is a very interesting example, right? So I was visiting one of these craft village, and there what they said was these potteries get broken and they'll have a huge loss. Around 50% of it is lost. So which means the revenue that the person gets reduced. So can you do something about it? Then we looked at the properties of the clay. Then we started mixing nanomaterials into it. Did a lot of scientific tests and things like this, and we found that the strength can be increased. So along with the strength, it also showed some acoustic properties. So then we created these kind of amplifiers, right? These are mobile amplifier, analog amplifiers. You can put the mobile there and it will amplify the sound, right? So those kind of a lot of practical things you can do. There is displays that you have done. Many, almost around 60 products were in various stages. Also do a lot of, as part of outreach, we are doing a lot of IC, open source IC design activities. So if any of you want to be introduced, any of the colleges or institutions want to get an exposure to that, write to us. We'll come to your place and do it. May not be immediate, but we'll come there at some point, right? Please do reach out. So this is another one. We had run workshops for PCB design as well as chip design for school kids. Okay, so this is students from 6th grade onwards. So 6th grade onwards, and people thought I was crazy when I said that. we had chipped taped out with school kids. Okay. So 3 or 4 of them are doing full-time, part-time internships with us. Already they have published a paper as well. Okay. So that is the thing. So if there are BTech students, BME students and PhD students like sitting there, you know, just catch up. Otherwise you will be out of job. Because these, I'll tell you, the seriousness the school kids have is unmatched. Okay, they are so much involved, they are so much serious. That level of seriousness I haven't seen in PhD students as well. Yeah, that is true. That is true. But you know, but it's not. I don't think it's. It's basically curiosity. The curiosity they have to actually learn. They don't put a pretense to I know this, I know that. They are there saying I don't know anything, and I just want to learn it. It's curious. So, so the approach we took was we didn't start with layout, you know, what you call like the schematic or anything. We started with physical design. We had a 3D models created of transistors to capacitors, everything, how it is laid out in the chip. So they looked at these models like Legos, right? So, so they get excited with the Lego thing. And then our task was to make them draw it. So we gave them a layout tool, drew them, you know, showed the 3D visualization. Then they were, you know, able to draw like a, you know, in a single day, they could they drew something like a ring counter. Ring counter from day starting in the morning, like 9 o'clock, by evening 6, we had the ring counter there. Okay. They don't know anything about, like, you know, so we had like some things like what is a NOT gate, you know, it's narrated as a story, like, you know, the NOT gate, OR gate, everything is narrated as a story, cartoons and all these kind of things. But that is something that anyone can learn, right? So logic gates are, you know, it's very simple logic. But for some reason, like going to the next level, it's a bit challenge. This is my team. Some of them had come for the APC cast. Yeah, you've seen. Okay, thank you.
DRDO. Sir, I had one doubt, sir. Are there any commercially available crossbar array devices, sir?
Yeah.
Okay.
Yeah,
which
so
company is making, sir?
So there is a company called Crossbar Inc. Okay. They have spin out, like, you know, so it comes from Wheelus Group in University of Michigan. So they had like a hafnium oxide based devices, like they had a crossbar, and from there they created this Crossbar Inc. kind of company. But these days you can actually get it from TSMC as well. TSMC also has a crossbar. But they usually, I mean, they don't give it. I think in India only I have access to it as of now. Yes, yes. So they are very, because it's still in that, what you call the final stage of commercialization for them. They want to make sure, like, you know, it's 100% right before they give it. But there are global foundries have got memristor models, devices as well. So if you get those, you can actually create those array. IMEC has, you know, been trying many things. So there's a few.
Sir, one more thing, that variability we discussed, sir. What about parasitics? How will we handle them in the design?
Parasitics, see, okay. So the write operations usually, you know, you don't need to have a very high frequency, right? So you can write it very slow. So most of these parasitic issues doesn't come there. Where you have is read operations. Read if you want to make it very, very fast. So there, like, you can do a lot of compensation. There are many compensation related techniques. So if you are doing analog, obviously your read amplifiers that are there. The problem is not just the parasitic, it's the offset. Offset voltage, input voltage of those op amps becomes kind of a challenge, because you cannot push it below a particular point. So there is a set of like tricks that you need to do to make sure it works. Then there is always, you can retrain the network, right? Because you are readjusting the weights, you basically can compensate for the changes that are there, because see it as like a conductance, right? So whatever the capacitive or inductive effect or the resistive effect that comes in, it is a additional conductance that come in the path or the to that of whatever resistive element. So you basically reprogram the weights to compensate that. That also.
Sir, is it possible to implement spiking neural networks?
Yeah. Most of these we have implemented spiking networks.
Okay.
So there are many ways in which you can do it. Usually, like, what happens is if you are training the spiking neural networks directly, the accuracy will be very low, even as in an algorithm, because people haven't still figured out an algorithmic way to train the spiking network directly. But what works better is, like, if you take a CNN, convert that to a spiking CNN. So you already have figured out the weights, and then you're translating those weights to spikes. That way the accuracies will be high. So any network can be converted to the spiking networks.
Very good afternoon, sir. Happy to see you back in Hyderabad. Welcome to you. I had 3 questions. First thing is models along with Memister. As you said, that is IMEC and Global Foundries are there. Is it Skywater open source is giving Memister models?
Yeah. So Skywater has an open source ReRAM, which is based on hafnium oxide. So it's a bit painful to work with, but you can still work.
It's painful to work it. Oh, extension to this question.
We fabricated it and it works.
Okay. If it is neural network, right, you are adjusting the weights. So you are also talking about MAC. And this can be a fixed point, like, or a floating point. It can be converted into fixed or floating point. How do we do it at challenging floating point architecture kind of stuff?
Right. So I know this whole business of fixed and floating point comes in because you are thinking it in digital. Yeah. Right.
But when you are analog also,
this is analog. Like, you basically don't have to worry about it. Right. So it's basically you have infinite points. So and the thing is, it's a number of levels. So it's a discrete levels. Right. So when you are having, say, a weight, say 3.1111, right? When you translate it to the discrete level, that 3.111 may be 3.1.
Yeah, you are taking out imaginary.
You will be taking out some of those.
Yes.
But the way you do that in analog is that you again retrain it. Because it's not going to be one, see, neural network is not, you're not reaching a global optima, right? Most often what you have is, you're stuck with the local optimas or close to global optima. So
software and hardware, so software algorithms talks something else, and hardware what it required is something optimum in different way, right? So there is a correlation again, the non-linearity will come. So algorithm is talking about the floating point.
We are talking only about hardware.
Okay.
So in hardware you have weights, and those weights you are updating, training, right? And it has to, so you will be again benchmarking it against not just accuracy, you are looking at area, you are looking at power, everything, right? So it's a multi-objective optimization problem as opposed to a single objective optimization. So in algorithm, when you do it, you are only looking at accuracy, right? Whereas in a hardware, you also need to look at, like, if you are going to change anything in the hardware, then will the area change, will energy efficiency change, all those things changes, right? So it's usually treated as a multi-objective optimization, and you try to see, in some cases in application, you don't want the accuracy to be dropped, then accuracy becomes one of the primary criteria. In some cases, you're okay with reducing the accuracy by, say, 0.5%, but you want energy efficiency to be improvements to be maybe 20% or 30%, then you take that also into account as an important parameter. So in hardware, it's a little bit more of optimization as compared to like a pure software optimization, but this floating point business doesn't come as a huge problem in analog. Where it comes as a major problem is when you are running it in digital with a number of bits being limited. That's where then you have to worry about the algorithmic issue of it. Whereas in this analog side, that is not a major issue because you are anyway, these are like analog weights.
Last question, sir. Field programmable analog array. So the kit is developed by Digital University or?
No. This is there is a company called Anadim that does that boards. You can get that. What we have done is we have taken the basic IP, like there are few chips, and then we build some
external added to with that board.
Yeah. So we had like arrays of like those chips put together, and then we had the FPGAs also like put together into a single.
You tested with open source of your tools with that board? Open source tools?
For that board?
Yes.
No, that is just a graphical level programming thing, right? So you have all these blocks and you can just put those blocks, you can model each of those blocks, like some mathematical models you can put in, right? So if you have amplifier, you can give the gain, it's like Simulink kind of interface, where you put all those. So it's a very quick way to see whether your, analog circuits and the digital like mixed signal designs, works. Without actually having to spend a lot of time, it's a quick way.
Thanks, Alex.
Yeah. Good morning, sir. Sir, either this memory star is a unilateral device or the bilateral device?
You have bipolar as well as unipolar.
Okay.
Both of these are there.
Can we use this memory star as an amplifier?
Not as an amplifier. So far, I think you cannot. There is a specific region called edge of chaos where the instability can come in and you will see the amplification behavior. So you would see these chaotic circuits like, they exhibit that. You have a signal out of nowhere getting generated. And so that way it does. But if you give an input signal and then generate, that doesn't happen. So usually it's within like a single DC signal given in such a circuit, like because of the behavior, dynamic behavior of the device, it will actually amplify that signal itself to create like all sort of different patterns. So in fact, there is a very interesting like area called like cellular neural networks, right? The cellular neural network, you can actually have shown like you can use these memory devices to build all sort of different cellular neural networks based on these edge of chaos behavior.
Sir, what is the input and output impedance of the memory star?
It depends on the devices. So you will find like devices which would have like 1K to 1 mega. In some cases, like 1 mega to 100. So you have all sort of different variants.
It depends upon the dielectric we are using, that input and output impedance will be changed.
Yeah, depending on the device material that goes
means
in. Yeah, so there
material.
there are many different types of materials, devices there.
Yes.
So it's a filamentary devices. Usually you have anywhere from say 1K to all the way to maybe 10 mega, 50 mega, like that.
Okay.
I'm Asif from Srinidhi. We talked about memory star, basically a two-terminal device which can regulate current through it and record it. But how it can be operated in a binary digital circuit where we'll have input of logic 0 and logic 1?
Yeah, so memory star is basically a memory, right?
Yes.
So which means you can have two levels of resistance, right? So you have a high resistance and a low resistance. So if you want to store it as a 0, you program it to high. If you want to store 1, program it as low. Now if I read the current, the current will be now two different currents, right? So if you have high resistance, you have low current. If you have low resistance, you have high current. So just by reading the current, you can just say that it is written as 1 or 0. Okay. And then you can also build like a logic gates as well with it. Just by looking at the switching, like if it's 1, 0, 1, there are many logic, way to see the logic. There is something called ratioed logic, where you don't need another gate. You can just look at the input and output and the programming of these devices to figure out the logic. You can also connect it as a neuron and a threshold operation on top of it, just a comparator, and you can create a generic universal cell which can do AND gate, OR gate, NOR gate, everything. So that's also, it's called a threshold logic gate. So that also can be done. So those are many ways in which.
I mean, it can act in switch now.
Yeah, yeah.
From minimum resistance to maximum resistance.
Yes, yes, yes.
Where we can represent logic 0 and logic 1.
Exactly. So
Thank you.
basically, it can be used as switch. It can be used as like, with combination. You can use it as a universal gate, or you can use it for memory.
Thank you, sir.